All right, welcome to Lecture 10. Today we're going to be talking about understanding remote sensing in aerial photography. These lectures are going to provide an introduction to the understanding of remote sensing in aerial photography. Remote sensing and aerial photography are such a large topic that there are many books and different courses that are taught simply on the subject itself. To learn more detailed information about these topics, it is recommended that you seek out one of these books or courses after you're done with this one. So let's first define the idea of remotely sensed data. Broadly speaking, within the context of GIS, there are two common types of remotely sensed data: aerial imagery and satellite imagery. Aerial and satellite imagery are both remotely sensed data because it records reflected energy from a distance. This remotely sensed information is useful for many reasons, such as a large area of coverage and a single capture. Its ability to look outside the visible spectrum of the electromagnetic spectrum, its geometric accuracy once it's been rectified to Earth-based coordinate systems, and the fact that it is a permanent record of a single snapshot in time. Let's take a look at a few examples of remotely sensed data to get an idea of what we're talking about. For our first example of remotely sensed data, we're going to be looking at this satellite image of the Middle East, the Horn of Africa, and India. This image clearly illustrates what is covering the land on this portion of the Earth. The brown represents sand and dirt, while the green represents vegetation. In one single image, so much information is stored about that portion of the Earth at that particular time. This is a satellite image of Iceland. Again, based on the colors and textures that are shown on this image, we can derive quite a bit of information about the environment in that part of the Earth. For instance, if we look at Iceland along the top edge, we can see the texture that represents mountainous terrain. Along the southern part, we can see large flat areas that are likely plateaus. And in other areas, we could see different fingers and things like that sticking out into the ocean. This next image is an aerial photograph that we've already seen of the port of Corpus Christi. In this image, we see great detail about different structures and ships that are operating and existing in and around the port. This image looks quite a bit different than the previous images. For one, you're probably wondering, what is all that red? In this image, the red is representing healthy vegetation. The healthy vegetation is red instead of green because this image is looking outside the visible spectrum. This is useful because, as you will find out in a later module, objects reflect different portions of the electromagnetic spectrum differently. It can tell us useful and interesting things that we would not be able to see simply by using our eyes to view the visible portion of the electromagnetic spectrum. Here's a true color image of the same exact imagery, but without the infrared lens. The circles are irrigation circles of crops. It's clear to see that where the crops are irrigated, they have very healthy vegetation. This next section, we're going to discuss the basic principles of remote sensing. The main idea behind remote sensing is the storing of reflected electromagnetic energy by a sensor that is distant from the object being sensed. The reflected electromagnetic energy is commonly referred to as light. Light energy is characterized by a wavelength, and each wavelength defines a distinctive color. Examples of colors would be red, orange, or yellow. As humans, we only see the visible portion of the electromagnetic spectrum, which is composed of smaller and longer wavelengths that surround the visible section. Examples of waves that are longer and shorter than the visible portion of the spectrum are X-rays, gamma rays, and radio waves. The full range of wavelengths is called the electromagnetic spectrum. So, what we usually do here is we would show you a series of videos that explain the electromagnetic spectrum from NASA's point of view. not from their point of view, but they're produced by NASA. Um, because you're probably already watching this on YouTube, we're not going to go into YouTubeception while I show you YouTube videos on a YouTube video. But please, if you have any additional questions or want to learn more about the electromagnetic spectrum, go into YouTube and then search for the NASA EM spectrum videos. There are these three topics that are listed here: introduction to the electromagnetic spectrum, visible light waves, and infrared waves that you can watch and learn a little bit more about that. All right, so moving forward, let's briefly reinforce some of the concepts of the electromagnetic spectrum that you've probably already learned in your physics courses. So the well, not probably learned, they were definitely taught to you. Maybe you didn't pay attention. I don't know. That's up to you. All right, sorry. So the electromagnetic spectrum is composed of energy at different wavelengths. The portion of the spectrum that we can see with our eyes is the visible spectrum, which is roughly between 400 and 700 nanometers. The infrared portion of the spectrum contains longer wavelengths than the color red, and it is quite useful when studying environmental features such as vegetation. And this has to do with what I was talking about in our past lecture uh, and the reflectance properties of chlorophyll and how we're able to monitor that and use it as a standard for plant health. So just generally in GIS and remote sensing, the visible and the infrared portions of the electromagnetic spectrum are the most widely used portions of the spectrum. As technology increases and we have more affordable, powerful sensors, we might start looking into different types of wavelengths that we haven't really been able to use before, like ultraviolet radiation or in the near red and X-rays and gammas and all these other things that we can't quite use yet in a practical sense. So now that we've spent all that time discussing the electromagnetic spectrum, because it is the reflected energy and where it lies within the electromagnetic spectrum that we are interested in recording. Electromagnetic energy, it's all around us and it is constantly striking objects. The energy is then going to be reflected, absorbed, or transmitted from those objects back to our recording sensors, such as a camera. The energy that is reflected is what appears in some of the slides we're going to look at coming forward. So in our visible spectrum, if an object is reflecting, say, the color green, that means it's absorbing all the other colors within the visible spectrum. So we will record the green wavelength for that object in our sensor, in addition to the energy being reflected from the visible portion of the electromagnetic spectrum. It's also simultaneously reflecting, absorbing, or transmitting electromagnetic energy outside of the visible spectrum. We may or may not see the electromagnetic energy outside of the visible spectrum based on which portion of the spectrum our sensor is going to be calibrated to. So in relation to reflecteds, here's a quick graph. Don't focus so much on trying to capture the different units. It was just a really good graphic that I feel like gets the point across. As we could see, we have solar radiation waves coming from the sun and traveling to Earth. Some of those, they actually get down to the surface of the Earth. From there, they're going to be reflected in different ways depending on the objects they're hitting them and what their chemical makeup is. And that's how we get to see color. Some of this stuff, it's going to be extracted inside the atmosphere before it even reaches the Earth. And that can have varying different effects on different things. In fact, if we didn't have things like the ozone absorbing some of this stuff, the Earth would not be a livable surface. So just as a few reminder on some of these basic principles is that electromagnetic energy strikes striking an object is either going to be reflected, absorbed, or transmitted every time. These are key things to remember about electromagnetic energy and how it affects what we're doing here in remote sensing. Do know that objects appear as the color they most reflect. If we see something that's green, it's not absorbing the green rays, it's absorbing everything else and reflecting it back to us so that as it passes through our eyes, we can see it. And that objects also reflect other portions of the spectrum. It's not all just what we can see. We're scientists here, we should understand this. There's a lot of other things that are happening in the background. So we'll now look at an example of an image taken on a farm in South Texas. This image represents the visible portion of the electromagnetic spectrum, and therefore the healthy vegetation shows as green. Based on what our eye sees, this looks like a perfectly healthy crop. Sure, there's some variations in color, but overall it looks good. However, if we took a look at the same time, at this crop at the exact same time, but focusing on the infrared portion of the electromagnetic spectrum, this image will show us what that looks like. So this image shows a different story of the crop area in the electromagnetic spectrum. Healthy vegetation reflects a large amount of infrared energy. That means that the brighter red areas are where the crop is going to be healthiest. Let's focus on the area at the bottom of the image. If you remember on the image of the visible spectrum, this was all green and it looked relatively normal. However, the energy reflected in this electromagnetic spectrum tells us that these are unhealthy plants because of unusually high salt content in that portion of the farm. So that's why the plant looks healthy on the outside, but inside it truly is a very unhealthy plant. So another thing to take a look at going back to reflectance is the difference between reflection and albedo. So reflection is the direct bouncing back of energy without being absorbed or performing any kind of additional work. It's simply what it sounds like. It's reflectance. Light comes down, it hits a surface, and then it reflects the color of the rays that weren't absorbed. Albedo is the reflectance quality of a surface. So an albedo of 0% means that nothing is going to actually be reflected, while 100% is going to be full reflectance. So a lot of when I think of like brighter, vibrant colors, they're probably going to have a higher level of albedo because it's actually giving back a color. We can use different sensors to see different things. Then when we have really, really dark objects, all right, all of that's going to be absorbed because black in its truest self is when light is fully absorbed. We get true black. So obviously at times there's always going to be some reflectance, um, but we are able to use this to our advantage in remote sensing. The Department of Defense used this heavily during World War II to try to locate German bunkers. So they would fly all across or fly and take imagery over different parts of France and Germany, and everything just red, green, blue would look like it's healthy, look like there's plants and, oh, there's a little grotto or a small group of woods here. But if we were able to actually look at the infrared values of it, we would get black readings, just solid, dark. And that would tell us that all that plant life that we see down there, that's actually stuff that's cut down and they're using it as cover so that we were able to identify machine gun nests and identify hidden bunkers and stuff like that to help protect the Allies as they were moving forward in planned operations as we were moving further and further into Germany. So something that's also important to realize is that different parts of the Earth have higher levels or lower levels of albedo, or the ability to reflect light. So you can see here a lot of the northern hemisphere, the upper parts of the northern hemisphere, and the Sahara part of Africa have very high uh, albedo levels. Well, that should make sense because up north it's a lot of snow. Sahara is a lot of desert. These are very light colors that are going to be reflecting almost everything, because just as we'll see black when there's no reflectance, white is absolute complete reflectance. So you kind of get it right. It makes sense. And then the other parts of the surface of the earth above the ocean, we don't have as deserts everywhere, so it's forests, things like that we're able to identify. So there are two types of remote sensing systems that we're going to learn about in this course: passive and active. The previous two examples of images taken of the farm in South Texas represent passive remote sensing systems. This is because the camera did not transmit any energy down to the earth to be reflected back and recorded. Instead, the camera relied on an external source of energy, in this case, the sun. Relying on an external source of energy has its positives and its negatives. The positive is that a sensor does not require any large amount of energy to use. The negative is that it can only record reflected energy when the external sources are available, and they may be affected by atmospheric conditions, and they're not going to penetrate things like clouds. Therefore, when sensing with passive remote sensing systems, it's important to plan far ahead to record when there is ample energy and little to no obstructions. An active remote sensing system generates its own energy signal, and that energy is sent out and returned. A major positive for active remote sensing systems is that it can collect data at day or during the day or at night, and it can typically penetrate clouds using wavelengths that are cloud penetrating. The negative is that it can require a large energy source to operate. As a quick challenge before we go into the next system, can you think of a well-known active remote sensing system? Enter your answer in the comments below to win $500 to Cabela's. No, I'm kidding. I'm not giving y'all shit if you know. Shouldn't have said that. So radar is an active system, and it is very well known. So radar stands for radio detection and ranging, and it works by transmitting radio waves and recording the intensity of the radio waves that are returned. Radar is the most common active remote sensing system in the world, except for cameras with a flash. Radar systems are typically restricted to one wavelength, so it can identify the radio waves that are returned as its own. Because of this, radar only records the intensity of the return signal. Therefore, it produces a monochromatic or a black and white image. So this is a picture of a radar system at Heathrow Airport. The radar tower rotates 360 degrees, transmitting a single radio frequency, and it measures the intensity of the returns, which represent airplanes in the area. The air traffic controllers can then use the resulting image to direct traffic coming in and out of the airport safely. This is the resulting image of a weather radar showing a hurricane covering the southeast coast of Florida. You can see here, this is from 2005, so no, it's not Michael, plus Michael hit way further up in the panhandle, in case you're wondering. So while this image has multiple colors, the colors are false, and they simply represent the intensity at which the radio wave has been returned to the radar sensor. Just like in your labs when you're assigning symbology to graduated simples, you're able to apply false colors in order to get a better understanding or a better reading of data that we're looking at. Because if this was just shades of black and white, it wouldn't be that useful. Don't believe me? Try to print it out. Another active remote sensing system is LiDAR. LiDAR stands for light detection and ranging, and has become a very, very popular active remote sensing system. LiDAR works by scattering laser pulses to find the range of a distant target. Because lasers produce higher frequency and lower wavelengths, they are much smaller than radio waves, and can provide a much higher resolution image. So you can look up all kinds of different videos on YouTube and things like that if you want to see LiDAR products. There's a great one done by Sam Inc. in downtown Austin, Texas. And it captures everything from leaves on trees to textures on top of manhole covers. LiDAR has come so far just in the past 5 years. It's amazing. But what I'm going to show you is a older example of LiDAR. So this example um, is LiDAR data that was rendered in 3 dimensions of the ground zero site from the terrorist attacks of September 11th, 2001. This was probably one of the first major uses of LiDAR by the government for something that was publicly facing. So in the lower center of the image, you could see where the two towers used to stand and how tall that rubble pile is. This image shows how detailed a LiDAR image can be from the air. And this is flown from an actual aircraft. Nowadays, we're putting LiDAR systems on vehicles, backpack-based deployments, as well as larger drones and things like that. All right. So for this next section, we're going to be talking about primary uses of aerial images, and then we're actually going to stop at the end of that because we're going to break this lecture into 2 parts because that's how it's actually going to happen in class. So for those of you on YouTube watching this that aren't part of my Introduction to GIS class, just look for part 2 or lecture 11. So aerial imagery has been a primary source for years. Hang on, I need to make sure that we're still recording. It just made a bunch of noise at me. I need to find out if it's still going. I'm gonna pause it. Okay, we're back. I think my battery's getting low on my headset, so I might talk a little fast here to make sure it doesn't die on us. So, like I was saying, aerial imagery has been a primary source of geographic data for decades. I'm currently working on a project with the Army Corps of Engineers in Galveston, um, digitizing and georectifying uh, about 100,000 aerial images of the Texas coast that date back to the 1940s. So aerial imagery kind of became a thing as soon as portable cameras were invented. And what we consider portable and what was considered portable are two very different things. Um, but it also became a much more practical practice of remote sensing data when airplanes came around, because before they tried doing it with kites and balloons and things like that, and it was very hard to get a steady picture. Aerial imagery also sparked the field of photogrammetry, which is the science of measuring geometry from images. So here you can see a portable camera that is being loaded up into a military aircraft in order to take um, aerial images for Department of Defense uses. Something like this would often produce images that look like this. So much lower resolution, but still a lot better picture of an area than you could get from the ground. Nowadays, we have much higher end cameras that are oscillating, that they can move, they can work with turbulence. This one here, it's attached to a helicopter. And helicopters, if you've ever ridden in a helicopter, they're not going to have a very smooth ride. So this camera is probably mounted as not just swiveling, but on a gyroscope, plus probably has an IMU in order to make corrections for some of the movement that's occurring from the helicopter. Here we're seeing a group of Marines launching um, a ballista launched SUAS for different operations. Uh, Nowadays, they have fixed wing SUASs that you can just hold above your head and throw, and it'll start taking off. And they also have very, very large ones like the Predator, which has its own engine and everything and could go for about 48 hours in the air. But coming back to this picture that we keep seeing of Corpus Christi, this is the kind of imagery and the data that we can collect from aerial imagery. And then we'll use photogrammetry to extract things from here. So like volumetrics of some of the stockpiles that we're able to see, uh, tracking different health or conditions of the different tanks that are existing in the area, or being able to just to monitor the number of ships that are going through if this is something that they're able to regularly do. So again, like I said, um, drones have become the hot item. Kids are getting drones for Christmas now with cameras on them, and we have all these amateur drone pilots that are out collecting imagery and using it mostly for art, but some people for science as well. So this one here is actually mounted to a kite, so it's not um, actually running on its own battery power or engine or anything like that. It's still using the just wind to get it up into the air, and then it's able to take pictures. These are really popular if you go to like South Padre Island for spring break. You're going to see people using these to take videos of everyone on the beach because a regular like quadcopter or octocopter isn't going to do so well on the beach because the winds are so high. It'll drain the battery so fast. So this is much more effective in this case. This is also the type of information that we're able to collect. So it doesn't always have to be about zooming way out. Here we're a lot closer to the ground, and we're getting a much higher resolution of things. We have a student right now in the Geospatial Systems Engineering Master's Program using UASs and LiDAR to help monitor rooftop health or rooftop conditions so that we can try to track where leaks or potential leaks are going to come in so we can solve problems before they become a problem. And then again, there's just always the great imagery that can be extracted with it. So aerial imagery is very frequently used just as a backdrop or something like that. So it's not always limited just to extracting specific data. It could just be looked at as enriching data or enriching features. All right, so I think we're actually going to stop here on aerial image attributes for the day. And then we'll come back. So this is actually a lecture for my Tuesday class. So those of you that are just watching this online, you probably won't see anything else coming through until Thursday for the other half of this lecture, where we will be talking about aerial image attributes, different types of use, quality, distortion, um, stereo images, and then satellite imagery, and some of the stuff that's done there, and then some of the pros and cons between the two. So I hope you've enjoyed this first part of our lecture on understanding remote sensing in aerial photography. Uh, if you have questions, feel free to post them in the comment section. If I see them, if I happen to see them, I will be happy to respond or point you in the direction of more information. If you're in my class, please don't use the YouTube comment section to ask me questions about class. Email me or let me know on Blackboard. All right, thank y'all, and I'll see y'all next time.